we introduce Cyrop, a method for in-the-wild face expression capture and retargeting. Cyrop captures and retargets facial expressions from in-the-wild videos. It handles extreme facial expressions and head pose and transfers the capture animation to new facial identities. Most existing monocular face capture methods rely on linear 3D morphable models, known as 3DMM. These models represent a face mesh as a combination of two independent factors, identity and expression. However, in these models, they are independent at the vertex displacement level. In reality, a semantic facial expression like a smile cannot be simply represented by vertex displacements that can be applied to any identity. That is, these deformations due to expression directly depend on the underlying face morphology, meaning the identity. We show here some examples of transferring vertex displacements from one person to another. This may lead to identity leaking, where traits from the source person are visible in the geometry of the target person, like the jaw on the left and the lips on the right example. They are also prone to artifacts, like in this last example. In this paper, we introduce an identity-aware expression representation that encodes the semantic of facial expression, which enable better capture and retargeting. In addition to not truly capturing the semantic of expression, existing monocular capture methods struggle to capture accurate 3D face meshes. While they show promising results when viewed from the original camera angle, viewing the 3D reconstruction from other angles reveals artifacts such as asymmetric mouth shapes and distorted expressions. This is a problem for applications where the mesh is viewed from arbitrary angle, like virtual reality and video games. We address this problem with a new method trained using a mix of synthetic and real data, where we train on ground truth geometry from synthetic data and generalize to real data using domain adaptation. We also propose a new benchmark for geometric evaluation of expression capture. We expect this to advance research on face geometry reconstruction from monocular images and videos. Let's first have a high-level understanding of our model. Given a monocular image, we estimate a semantic expression representation and apply it to a neutral mesh of the subject. Our model also allows for retargeting the source actor's performance to a different individual, just by applying the same code to the neutral mesh of another person. Let's see how the semantic expression model is trained. We train the semantic face expression model on the reconstruction and retargeting tasks. The first objective is to encode the expression into a latent code and decode this code to the same individual. The second objective is the retargeting task, where we apply this expression code to a new person. We use a cycle consistency loss in order to encourage the expression to be consistent across individuals performing the same expression. Therefore, our method can be trained without the use of paired expression data. More details can be found on the paper. Now, we show how we train the face expression capture model. This model learns to estimate the semantic expression code given a single monocular image. To this aim, we use a mix of real and synthetic data. With the synthetic data, we apply a code loss for which the ground truth target expression code is available. To enable generalization to in-the-wild images, we add two loss functions. First, the model predicts landmarks as a shared task between real and synthetic images. We use a domain adaptation mechanism to bridge the domain gap. We add a classifier CD that is trained to distinguish between real and synthetic images. We use gradient reversal to encourage the learned features to discard domain-specific information, thus aligning the distribution of both domains more closely. Before we show results, we introduce a new proposed benchmark called MultiREX, based on the multi-face datasets. This is the first video-based face expression capture benchmark assessing for geometric error. It includes videos from 8 people under 5 different viewpoints and allows to evaluate monocular capture methods with different head pose and extreme expressions. We designed a region-based evaluation methods by dividing the face into 4 regions and performing region-based rigid alignment before assessments. This allows for a robust evaluation of the expression capture on different parts of the face. We provide the code and assets for evaluation of any flame-based models on MultiREX. Let's have a look at some results, starting by results on the MultiREX benchmark. We present here the face expression capture for EMICA and our model, considering a frontal and a side view. We observe that our model produces more expressive results and displays more consistency across views. We present some other views and methods in the paper. In this next experiment, we compare our method to the state-of-the-art models on their ability to retarget a source expression given an in-the-wild monocular video. We observe that our method is more consistent over time, but also that some key expressions are better captured by our model. By extracting the expression semantic and having an identity-aware model, Cyrop is able to retarget convincing facial motions with respect to the face morphology. For quantitative results, additional qualitative analysis, as well as a more in-depth explanation of the methods, please refer to the paper. Thank you for watching this video.